UDP is a very simple connectionless protocol. In fact, applications that run on top of UDP have to provide their own sort of sequencing and acknowledgement system, retry timers, and timeout values, because UDP doesn't provide any of that. Most commonly on networks, we'll see UDP in use for DHCP and DNS communications. I'm going to open up a trace file right now called DHCP boot, which is just a standard DHCP 4-packet sequence. We have discover, offer, request, and acknowledgement. And DHCP uses UDP by default. We always have to assume that if an application is communicating to the broadcast address, it's going to be going over UDP. It's not going to be going over TCP. We're not going to make TCP connections to anyone using the broadcast address. The same thing is true for multicast style communications. If an application uses multicast communications to communicate to clients, it's not going to use TCP, it's going to use UDP. So let's look at the UDP header structure. First of all, we know that UDP is coming up next because when we look in the IP header, we'll see the protocol value of 11 in hex, and that indicates that UDP is coming up next. The UDP header is only 8 bytes long. It has no capability of having any options or ever being any longer. I'll open up this UDP portion here, and here we can see we have the 2-byte source port field, we have the 2-byte destination port field, we have the 2-byte length field, and then we finish it up with simply a checksum area. Now, although this area in Wireshark appears like there might be some fields underneath it, there really aren't. These are just checksumming pieces built into Wireshark. So Wireshark will look at this packet and tell you whether the checksum is good or the checksum is bad. And when we get into the filtering section, the next section for UDP, I'll show you how to filter on invalid checksums. So that's the entire UDP structure. Now, the length field in UDP is giving you the length of the UDP header, the 8-byte UDP header, plus any valid data that follows. So this indicates that we have 100 bytes of data sitting in the bootstrap protocol area. 8 bytes of data is in the UDP header. Now let's correlate that with the IP header value of total length. The total length in the IP header will be the IP header plus anything that follows, any valid data that follows. The IP header is 20 bytes long. We know that the UDP header is 8 bytes long, and we know that the payload is 300 bytes long. So this total length value does work, and it matches up with what UDP is saying. That's it. UDP is that simple. In the next section, we'll go through building capture filters, display filters, and some individual field filters, as well as a filter to look for invalid checksums in UDP communications. In this section, we're going to start out by building a capture filter looking for all UDP traffic. Then we'll go into building display filters looking for all UDP traffic. And then we will build specific display filters looking for values in certain UDP header fields. The first thing we'll do is we'll build our capture filter for UDP. So I'm going to click on the capture options window. I've already got a filter in there and I want to get rid of that. I'm going to go to my capture filter list to see if UDP has already been pre-built for me and delivered with Wireshark, and it is. You can see that you don't even have to build it, but there's the filter string. In the capture filter area, Wireshark understands some very simple protocols such as IP, UDP, ICMP, TCP. So this is one of them, which is nice. So I'll click OK. And now I'm capturing, looking for any UDP traffic. Now I see I just received a DHCP packet in here, and I'm going to go over to a browser session because I know that DNS uses UDP. Most likely you'll see UDP in DNS communications and in DHCP communications and SNMP communications. So I'll toggle over to a browser window and I'll browse to some sites. eBay.com, you never know what's for sale today. Let's go to google.com. and www.espn.com. There. Now each one of those web browsing sessions to those different locations should have given me a couple of DNS packets at least. a DNS packet to get to the primary site, but also if they had some ad sites that they were pointing me to, I'd probably see DNS queries go to those other ad sites. Let's go back and see what traffic we captured. Back in Wireshark, I can see there's all that DNS traffic. Oh, look, there's a lovely little net bias communication. I'll scroll down. We can see eBay going out to the eBay site. There's another there's a little ugly messenger packet. We're still going to different ESPN sites. We're doing all the DNS lookups. And ESPN is one of those sites where you think you're going one place and you're actually going a lot of different places. So we see all of the DNS traffic is being caught just by that simple filter. Now I'm going to stop capturing. And at this point, I'm going to build a UDP filter to pull out traffic from an existing trace file that's just UDP traffic. So I'm going to save this trace file first. I'm going to call this UDP general.pcap. Now, I don't have to say anything about displayed because I didn't have a display filter on this traffic yet. So I'll click Save. Now I'm going to open up a trace file called Nessus. Now this is a Nessus penetration test. And in this test I have all sorts of traffic. I have TCP communications, ICMP communications, UDP communications. And if I wanted to pull out just the UDP communications, I'll just type in UDP on the display filter line. I'll click Apply. And now I'm just seeing UDP traffic. Or so it appears. Now this is interesting when we apply these filters. The reason is I've got some ICMP packets in there. Now ICMP does not have either a UDP header or a TCP header. ICMP sits right after the IP header. But these are the two-headed ICMP packets that I mentioned in the ICMP section of this class. In this packet, we not only have the ICMP portion, but it's sending back to us our UDP header that triggered this response packet. So if we wanted to get rid of that and truly see only UDP traffic, we would have to add to that filter. I actually like having that in there because I'd like to see what type of responses the UDP traffic has generated. But if we want to get rid of that, we could say UDP and not ICMP. Now let's apply that. Now we've gotten rid of all of that ICMP traffic. Now I like that filter, so I'm going to save it. I'll give it the name of UDP only, no ICMP. Click the New button. We can now see our new filter sitting at the bottom of the list. I'll say OK. Now, in addition to building a UDP display filter, a standard UDP display filter, we can also filter on specific fields inside of the UDP header. In this packet, perhaps I want to filter on any traffic going to this port number here, 1701. Very simply, I can right mouse click and prepare a filter based on the selected value. Places it up above. We have udp.dst port. We also have udp.src port to do source port. I'll apply. Now these are the packets that have UDP destination port 1701. And again, you see our ICMP traffic will show up again because of the fact that it has that duplicate header in it. It's got that another IP header in it, and it's spitting back to us the UDP header that triggered this packet. If you wanted to get rid of that, you could simply say ampersand ampersand not ICMP, and then we would apply. Now we got rid of all of that ICMP traffic. We can also look inside of these packets and see that there's some analysis done by Wireshark, defining whether the checksum is good or the checksum is bad. I'll highlight the good checksum true line, right mouse click, and prepare a filter based on the selected value. Now, if a UDP checksum that's good has the value 1 assigned to it, this is just Boolean, a 1 or a 0, then if it's bad, it's going to have a 0 assigned to it. So I'm going to apply that, see if I have any packets. No, they all appear to have a good checksum. If I wanted to find all the good checksums again, I'll bring it back up. So that's a very simple way of building a filter looking for UDP communications with bad UDP checksums. Now, if you'd like the list of all of the available display filter names, there are two places you can go. One would be over the Wireshark webpage. On the Wireshark webpage, simply go to Documentation. As you scroll down, you'll see the Display Filter Reference area. We click on that, and on the index, I'll click on the letter U to see all of the protocols and applications that Wireshark decodes and has display filtering for. I'll click on User Datagram Protocol, and as I scroll down, I'll see the list of the field names. And there aren't that many, as you can see. You've got the length field, the port, source port, destination port. Now, if you don't care if it's source or destination port, you would just use udp.port ==. We've got UDP checksum bad. We used UDP checksum good, which is an additional one. And you saw that we just flipped the bit to make it bad. And then we've got the UDP checksum value itself. Another location you can go is in the expressions list. Back in Wireshark, I'll just click expression. And then I'll type in UDP. Open this up. And you can see all of the expressions that we can use for filtering on UDP traffic. So there we can see there's port is equal to, and let's put in a value of 67. Say OK. Now remember that it's going to append it to the existing filter up here. So if you didn't erase that filter, you're going to come up with a red line, and you'll need to erase it just as I did there. Click Apply, and there we go. We have two packets that have UDP port 67 in it. Again, that second one is ICMP, simply because it's restating the problem. And there's our port. There's our boot P server port. So filtering is very simple with UDP, but UDP itself is extremely simple as well. As far as looking at normal UDP communications, it's pretty simple because, again, we're only dealing with an 8-byte header. There's no sequencing and acknowledgement. There's no guaranteed delivery. There's no retransmission system set up. If you see a UDP communication go to a target from an application and there's no answer, and the UDP communication asks again, it's the application that's actually sending out that retransmission. UDP itself is not smart enough. So when you see retransmissions, retries, things like that, and then finally a timeout where the application has tried to send a request across over UDP 10 times and then has given up, this has nothing to do with UDP. UDP is just simply the messenger. UDP has no idea what's going on. And the rate at which the retry happens and the number of retries that occur is entirely up to the application. So UDP itself is extremely boring. I'm going to open up just standard DHCP communication. This is DHCP boot.pcaps that I'm opening up. Here we see the 4 packets. And again, if there's a communication that's going to go out broadcast or it's going to go out multicast, it better go out UDP. We don't want to see that stuff going out TCP. So that's where we would expect to see UDP communications. Now this is kind of an interesting one just because we have assigned ports for both sides of the communications. In DHCP we have the boot P client port number at 68. We have the boot P server port number at 67. And most of the time in communications we will have a definite port number used for the application on the server, but the client would use a dynamic port number. So in this case we've got a set static port number used for both sides of the communications. We have our length field saying that there's 300 bytes of data and 8 bytes of a 8 bytes of a UDP header, and then our checksum looks correct. We get a reply back and the source and destination port values are swapped. Here we can see that it's 270 bytes. That includes the 8 bytes for the UDP header, so that means the data is 262 bytes following this. And then we see another packet go out. I know DHCP is a little bit strange, and in the DHCP section we'll talk about this broadcast issue and what happens when you try to do filtering. It can be kind of a pain if you're doing some filtering based on a MAC address. And then the communication ends up and everybody's using their proper IP addresses now, and there's the UDP header. Everything is very, very simple. I'll open up a DNS communication. This is just, I'm going to open up DNS-MISC miscellaneous. Here we can see a DNS query going out, and there's our UDP header. In this case, we have a client that is using a dynamic port number going out to the DNS port number 53 on the server. Very, very short packet here, length being 41. That's 8 bytes for the UDP header, and the rest of it is data. And then when the response packet comes back, the port number values are swapped. So normal UDP communications are pretty plain and ordinary. Remember, however, that if we use that UDP filter on traffic that might have ICMP destination unreachable port unreachable communications, we'll be able to pick up that ICMP destination unreachable port unreachable communication. So up here I'm going to type in UDP. Now, unlike TCP, in the world of TCP, if you try to make a handshake to a port that is not active on that server is going to turn around and send you a TCP reset. But in UDP, you send a communication across to a UDP port number at a server, and if it doesn't support it, you'll get back the ICMP destination unreachable port unreachable messages. And we don't want to see too many of those. In the next section, where we go through analyzing unusual UDP communications, we'll focus a little bit on this, as well as a number of other UDP communications that you probably don't want to see on the cabling system. So this would be considered abnormal communication, but I just wanted to show you that it is typical that if you do send a packet out and that port is not active on the target, what should happen is you should see an ICMP destination unreachable port unreachable. That's the normal behavior for the protocol. Now, in the last module, we finished up by looking at this communication, this Nessus scan with a UDP filter applied. And this is something you really don't want to see on your network. Too many of these ICMP destination unreachable port unreachable messages. And if we just apply that UDP filter, we'll not only get the UDP query that goes out, such as this DNS query to 192.168.1.123, but we'll also see the ICMP response saying, I'm sorry, destination unreachable, port unreachable. But you don't want to see too many of those on the network. It might indicate one of two things. It could be that the client is misconfigured, and for some reason this client seems to think that .123 is the DNS server. Or it could be that someone is doing a UDP port scan, which is the case, which is what's happening in this trace file right here. As part of doing our Nessus scan against the target, Nessus ran a UDP port scan looking for services on specific ports. The DNS port 53, port 9101, the port mapper port, etc. So we don't want to see that kind of traffic on the cabling system. In addition, as we scroll down, you'll see some SNMP get next request communications going out to 123. And in this case, if we look down in the hex portion, we can see a word in clear text. Now that word that's in clear text is the community string that's being sent across the cabling system. This is somebody trying to get the SNMP data off of an SNMP agent by sending a community string. And they're trying the community string of private first. And as we scroll down, we can see they try public, secret, Cisco. There's a SIP communication. There's write is another one, test. And that's something we really don't want to see. All of those communications are going out to SNMP port 161. So those are things we definitely don't want to see. In addition, you might consider how much net bias traffic you have on the cabling system. If you don't need net bias on your network, just like if you don't need WINS traffic on your network, get rid of it, disable it everywhere. And you may see net bias communications going over UDP hitting port 137. Here's an interesting communication. This is a multicast DNS communication going out on the cabling system. It's not going to the multicast address though. One of the times you'll see a lot of that is if you have BitTorrent somewhere on your network, you'll be able to see a lot of MDNS communications related to BitTorrent. There we can see the ICMP destination unreachable packet. Now, the interesting thing with this packet is we're looking at this packet and wondering, well, what does this have to do with anything else that we saw in our communication? Because this packet doesn't seem to have a pair. It's all of a sudden way down further in the communication. It's an SNMP packet that triggered this. We can see that. We can see an SNMP packet right here. There's the UDP header that's being spit back to us. And there's the SNMP portion. We can open that up. Now, because of the rate that the Nessus system is sending these queries out, the target system is unable to keep up with sending back ICMP destination unreachable port unreachable communications. So if we scroll down further, all of a sudden we will see a whole bunch of these trying to catch up with the earlier set. So it's a little bit behind, and as the trace kept running on, these destination unreachable port unreachable messages were a little bit behind in most of the communications. Now remember, you can go into statistics and look at the conversations information and pull out all the UDP conversations in one shot by clicking the UDP button. We can see that there are 128 UDP conversations seen. We can sort based on the byte count to see which ones actually possibly transferred data. We can see this one right here at 1650 bytes. That would be something I might want to look at. We can see SNMP, and we saw that they were sending across the community string. I'm going to close this window out, and I'm going to open up another trace file called UDP echo. I'll clear my filter though, so we can see all the traffic. Now this is definitely something you don't want to see on your network. Unless for some reason you are using the UDP echo process for something, I wouldn't want to see this on the cabling system. UDP echo is kind of like a ping communication, but it goes on top of UDP. UDP echo communications use port 7, just as TCP echo communications use port 7. And by default, we typically have this disabled throughout the network. Anything that sits in the echo data will be echoed back to the sender. So there's a UDP echo request, and unfortunately we have a device that is responding positively. And that's not something that we would want to see on a network at all. The next trace I'll open up is called TFTP. Now, if you don't intentionally set up your network to support TFTP and you don't have any reason for people to use TFTP, you don't want to see this traffic on the network because this is trivial file transfer protocol. This is actually part of the reinfection process for a system that was infected with malware. When the system would boot up, it would perform all these different operations, and one of those operations was to go out of the network using TFTP to go get a file to reinfect itself. So here we can see there's the read request. There's the read request second packet. So we can see the first packet asking for the data. There's a second packet asking for the data. Now why we had to do two? It might be because we didn't get the answer we expected. So the application went and made another request on the cabling system. Then we finally see a response packet coming back, and then we see the acknowledgement packet. Now the acknowledgement here is done by the upper layer. This is done by TFTP, by the application itself. UDP has no capability of doing sequencing or acknowledgement. Now one of the things you can do to see what type of traffic you have running on the cabling system would be to look at the protocol hierarchical statistics. So I'm going to open up a trace file called evil program. And in evil program, I'll select statistics and protocol hierarchy. And I want to see what's running over TCP and what's running over UDP. In this case, I see there's UDP. Now, I expect Bootstrap protocol to show up because that's DHCP. I expect DNS to show up, but I don't like to see DCE-RPC show up. And it tells me that I have 13 packets that are DCE-RPC. Then I have some packets where I've got UDP with data transferring across the cable. So I don't like seeing that at all. I'll now open up another trace file called client dying, and I'll look at the protocol information on that one as well. So here there's our IP header, there's TCP, and I don't care about TCP, but there's our UDP communication, and there's our TFTP. That's the trace file that I pulled that TFTP filter out of, all that TFTP traffic out of. So by looking at the protocol hierarchy statistics, you can see what UDP is used for on your network system. And watch out for applications that you don't want to have running on your network, such as echo and maybe even TFTP. The last trace I'm going to open up is called UDP traceroute. Now, just as we can run an ICMP-based traceroute, there's also a UDP-based traceroute. And in this case, we see a DNS query goes out on the cabling system and a successful response comes back. And then we see a UDP packet going on the cabling system. We get a time to live exceeded message coming back. Anytime you get that time to live exceeded in transit, you should kind of suspect that you might have a traceroute operation happening. I'll go up into the IP header. Let me go back to packet number 3. And in the IP header, I'm going to look at the time to live value. And sure enough, there it is, with UDP sitting after it. Not ICMP. This isn't done with a ping. This is a UDP-based traceroute operation. Go to packet number 7, and we can see the time to live is now at 2. We can go to packet number 11, and we can see the time to live is now at 3. So this is a UDP traceroute. So if a company has blocked ICMP echo requests outbound and ICMP echo replies inbound, somebody can still ping a target, do a connectivity test to a target using UDP. And this is another piece of traffic that you may not want to see on your network.